Okay, so today's lecture is going to be about database storage, part one. This is the first of a two-part lecture. Just before we get going, a few housekeeping things. So homework one is going to be due on Sunday, September 12th at 11:59 p.m. Project number 0 is also due Sunday, September 12th at 11:59 p.m. And project number 1 will be released the following day, Monday, September 13th. A few other things, unfortunately, you may have noticed DJ Mushu couldn't be here with us today. He's actually out on the West Coast in LA. I don't want to get too much into details about it. He has this long-standing beef with a crew out there, so he's trying to get that wrapped up, and he should be back in class on Monday. The other thing, the office hours should be finalized now on the website. A few of them have switched to Zoom only, so you have a more remote-only options if you'd prefer. And we also created a Google Calendar, which is now posted on Piazza, that shows office hours, deadlines, those sorts of things. Okay, so that's all the housekeeping stuff. Are there any questions about anything related to that before we get started with the material? Great. Okay, so just kind of a high-level recap, an overview of what we've talked about so far. Mostly we've been focused on the high-level or application-level side of things. Topics like the relational model, SQL, query languages, how an application or an end user would interact with the DBMS. So kind of now our focus is going to shift for the rest of the semester about how to build the software that actually manages the database, so how to build a database management system and kind of go through all the different layers of that. So I showed a slide that was similar to this in the very first lecture, and kind of it breaks down the different high-level pieces that we're going to cover in the course. So we've already kind of talked about the high-level idea of relational databases and query languages, and now we're going to dive down into each layer of the system. So starting with storage, working up to query execution, concurrency control. So if you have concurrent transactions or queries that are executing, how do you manage that? Recovery, if your system crashes, how do you recover from a failure? And then some more advanced topics at the end. But so that's kind of the high-level outline. The other way that you can think about it is sort of this software stack diagram that's shown on the other side of the slide, where kind of the base layer is the disk manager, and we build additional layers on top of it. So each one of these blue boxes corresponds roughly to a self-contained part of the system. So each one of these boxes represents kind of an abstraction that each upper level in the stack can kind of call on and interact with. Doesn't need to worry about the implementation details of the layers below it, but it can still have some kind of API where it gets what it needs from those layers. So not everything is, perfectly clean cut. They're not all. Sometimes certain layers will need to interact with each other or know what's going on at a finer grain level. But in general, the system is designed to be modular such that you can build these layers one on top of the other, and you don't have to know necessarily low-level details of the underlying layers. So the topic of this lecture and the next lecture is going to be specifically the disk manager component that manages how the system is going to interact with the underlying file system. So kind of the whole premise of this course is going to focus on what we refer to as a disk-based DBMS architecture. And what that means is that the DBMS is going to assume that the primary storage location for all of the data in the database is on some non-volatile secondary storage. So you have some persistent storage medium like disk or SSD or something like that. And the DBMS assumes that all of your data lives on that storage medium. So the components are going to manage specifically the movement of the data, the database files, to and from whatever your secondary persistent storage is. So the DBMS is going to handle reading from and writing to the underlying disk. So it's helpful to think about kind of the, at a high level, how the storage hierarchy in a system works. So kind of starting at the top, you can get all the way up to like the CPU, and at the very bottom is the kind of lowest form of storage. And it's helpful to think about kind of the trade-offs that you get with each one of these layers in the hierarchy. So at the top, again on the CPU side, it's much faster to access data if it's in CPU registers or CPU caches, but the available space that you have to store data is a lot smaller, and it's much more expensive per byte of data that you store. And as you go all the way down to the lowest layers, it becomes much slower to access data, but you have a lot more space, and it's cheaper per byte. So the important distinction that we're going to make in the course is between volatile and non-volatile storage. So volatile storage, you typically can access data randomly, and it's byte addressable. But the problem is that if you remove the power source, so if you trip on the plug and it gets unplugged, or the power goes out, or for whatever reason the system crashes, you're going to lose all of the data that you have sitting in your volatile storage. On the other side of the line is non-volatile storage, which is typically block addressable, so you can't necessarily access an individual byte. You can get rather a block of data, a block of a range of bytes. But the benefit is that if the power goes out, all your data is safe. So power can go away fully, plug it back in, and all the data is there. So kind of this split here is the important part we're going to care about for correctness guarantees in our system. So anytime that we talk about DRAM, we're just going to refer to it as memory in the course. And anytime we talk about any kind of disk or persistent storage, it's anything that's non-volatile. So it could be SSD, it could be a traditional hard disk, it could be some kind of network storage, whether that's like a distributed file system like HDFS, or if you're on the cloud, maybe like Amazon S3, just something where you have network accessible storage. So kind of just memory is volatile and disk is a non-volatile storage. And then there's also some, as I mentioned, higher level CPU storage, but for the purposes of this course, we're not really going to be concerned with that. So this is kind of the traditional hierarchy. There are other storage modalities. So for example, if you have fast network storage, we're not really going to be too concerned with that. There's this other layer that kind of sits in between DRAM and what you would consider persistent storage, called non-volatile memory. The marketing people decided it would be better to be called persistent memory, so you might see that now. It's kind of interesting because it gives you a lot of the same properties as traditional DRAM, but if you remove the power, it retains the data. So there are some trade-offs. It's more expensive than some other forms of persistent storage, and it's slower than just a regular DRAM, but it gives you the byte accessibility, and also you don't have to worry about losing your data. So Andy actually, and his first PhD student, Joy, actually wrote a book about non-volatile memory database management systems, kind of how to redesign the stack to benefit or best leverage from non-volatile memory. And there are increasing numbers of products being released. This one's from Intel. For a long time, there was this sort of constant promise of non-volatile memory out there. The marketing people always said it was coming soon, but soon never really came. So it's kind of been in this perpetual limbo, but more and more products are starting to come out, and maybe, I don't know, within the next 10 years or something, it might become more commonplace. But for now, we're not going to worry about it because it's not common in typical deployments. So another way to think about kind of the storage hierarchy is to consider the access times for each layer in the stack. So at the top, you have the CPU caches, and those take like on the order of nanoseconds. And on the very, very bottom is tape archives, which is like that's 1 billion nanoseconds. So these numbers are kind of difficult for humans to wrap their heads around. So if we convert it to a little bit easier time scale, if you think about it, normalize it to like seconds, on the top, reading from the CPU cache is like half a second. And on the very bottom, if you want to read from tape, that's going to take you like 31, 32 years. So this kind of storage hierarchy is going to be important because as designers of the DBMS, it's important for us to consider the access latencies to the different levels of the storage hierarchy where data can live in the system. So maybe another helpful way to think about it from a famous database researcher, Jim Gray. His analogy was in terms of like if you want to read a page from a book right in front of you, that's like accessing at the highest layers in the hierarchy. Going to disk is equivalent to going to like Pluto, and then if you want to read from tape, that's like going to a different galaxy altogether. So again, this is going to be really important just to keep in the back of your mind when thinking about the design decisions in the system. So I also mentioned that there's this distinction between sequential versus random access. So typically in memory, random access is okay. You can access a random offset in an array, and it's not too bad. Sequential access might be a little more performant, but there's virtually no difference between them. Whereas if you're accessing data stored on a traditional hard disk, because of the way the disk read head has to move to access data on different platters, it's more beneficial to do sequential access. So the DBMS kind of design we'll be focusing on is really going to need to consider these access patterns, sequential versus random. So the algorithms, a lot of the algorithms we'll look at are going to try and maximize sequential data access for contiguous data blocks at all costs. And kind of the allocating multiple pages at the same time in like a contiguous range is referred to as an extent. So kind of the design goal that we're looking at here is to allow the DBMS to manage a database that exceeds the amount of memory available. So this was especially important a long time ago when memory was scarcer than it is now. But if you have a really large database, you're still running Cool. Okay, let's get started. So today's class is about database storage part 2. So it's a continuation from last week's lecture where we talked about kind of the low-level implementation details of storing data in the database management system. Before we get started, just a couple administrative things to check off. So project number 1 is going to be released today. I'm not going to talk about it in today's lecture because actually the piece of the system you'll be implementing, the buffer pool, we're going to discuss in the next lecture on Wednesday. So I'm not going to talk about it today, but it should be released to you if you want to take a look by the end of the day today. So the second piece, project number 0 was due last night at 11:59 p.m. If you'll recall from the previous lectures, the first lecture and the last 2 lectures, and also on the website, it was explicit that if you didn't or weren't able to complete the project by the deadline with a score of 100%, you're not going to be able to continue in the course. So that's administrative assignment stuff. One other thing is that there will be the database tech talks starting today, this afternoon, right after class actually. The website is there, and we're going to have different people come every week. They're all on Zoom, so you can just join the Zoom call. All the information should be on the website for how to join, and they're not like marketing talks. They're like really low-level tech talks, so you can kind of see how some of the topics and concepts that we cover in the course are being applied in real-world systems. So if you're interested in those, feel free to join the talks. So if you'll recall from last lecture, we talked about kind of the focus of the course is going to be about this disk-oriented or disk-based architecture. So in that, we assume the DBMS has its primary storage on some kind of non-volatile disk. That could be a regular hard disk, it could be an SSD. But the key idea is that the storage medium that is the primary location where the database lives is on some kind of non-volatile storage. So if we remove the power, that means that we're going to keep all of the data that we have in the database. We're not going to lose it. Whereas if it's in memory or the CPU cache and we get rid of the power, all our data is gone. So kind of the DBMS rather than the OS, and we talked about why it's important that the DBMS manage this process, but the DBMS is going to handle all of the data transfer between non-volatile and volatile storage. So from disk to memory and back again when we want to persist our data. So just to kind of recap some topics we talked about last time, the idea of slotted pages is a common layout scheme in database systems where what we're going to do is we're going to map individual tuples in a page to these slots. So you have the slot array along the top, which is going to handle the offsets of the tuples, and then we have fixed and variable length tuples along the bottom that the slot arrays are going to point to. So we have pointers in these slot arrays, and that allows us to fill up pages with variable size tuples. We don't have to worry about finding the location of individual tuples inside a page. So again, these two, the slot array and the tuple data at the end of the page are going to grow towards each other in the middle. Just give me 1 second here to make sure. Okay. Okay. So kind of an alternative storage approach That's the slotted array page approach. An alternative storage approach is what we call log structured file organization. So rather than storing the tuples, the data directly in the pages, the DBMS is only going to store basically log records. So by log records, what I mean is logs of what data we're inserting and how we're updating the data in the system. So every time, for example, we're going to insert a new tuple, we're going to store that as a log record in a page. If we want to delete a tuple, all we do is we mark that tuple and the page is deleted. And if we want to update something, we just add a log record to the page that specifies which is the data value that we updated. So what this is going to look like is, again, we're going to have a page, and we're just going to go through and start appending these new entries as we make changes to our data. So you'll see here we're inserting a tuple with ID 1 and value A. We insert another tuple, ID 2, value B. We delete a tuple with ID 4 and so on. And kind of rather than storing the actual values, we're just storing these sort of log records that specify the changes that we're making to the tuples in the database. So can anyone tell me why we might prefer this storage layout versus the other one we talked about with the slotted array layout? Like what advantage would this sort of storage layout have over the... That is correct. So you're going to get really fast writing with this, because you can just, rather than having to go and update individual tuples in a page, you can just append the log records to the end, and it's really fast to write. It's also great for disk I/O because if you recall from last class, we talked about the advantages of having sequential writes versus, or sequential reads or writes versus random I/O. So in this case, since we're always appending to the end of the page, you get much better sequential performance. So of course, if we get fast writes here, then on the other side of things, it's going to become a little bit trickier to do reads. So to read a record, what we have to do is essentially scan this log backwards in order to recreate the tuple that we want to query. So for example, in order to reconstruct, let's say tuple ID 2, we have to start reading the log record back, and we say, okay, we're updating the value to value Y, and then we go back further and we get the other potential attribute values for that tuple by reading back through the log records. So we kind of have to do this reverse scan over the log to reconstruct the tuple by applying basically all of these log records along the way. So of course we can do different optimizations, like we could build an index that would allow us to jump into the log just to find the different log records that apply to each of the tuples, so that way we don't have to do a full scan through all of the log records. We could just, for example, if we want to find all of the log records that apply to ID 2, we can go through and just pick out those individual ones. That's okay, but again, now you have to have this additional data structure where you're maintaining kind of these offsets to go find the exact log records for particular tuple. Yes? I'm sorry, could you repeat the question a little louder? Why is it back? So the question is, why is the scan through the page backwards and not forwards? I guess that you could implement it either way. It doesn't really matter. I think there are certain conditions where it may be more efficient to implement it one way versus the other. So for example, if you're scanning backwards and you get, as soon as you hit the insert, you know that you're done. You don't have to scan any further backwards. Whereas if you're scanning forwards, you may have to scan, I mean, you would have to scan all the way to the end of the file because you don't know if there are any other changes or update log records that are coming in the future. But if you scan backwards, you could, as soon as you see the insert, or perhaps even as soon as you see like a delete, you could just abort your scanning early. You don't have to continue all the way to the beginning. Does that make sense? Yes?
If we were replicating the database, would a log structured file organization be more advantageous than a slot map or slot array?
So the question is, if the database is replicated on several machines in a distributed setting, would a log structured file organization be more advantageous than the slotted page array? I think it depends on a lot of factors. I think that probably the biggest advantage to the biggest reason you would choose a log structured layout is based on the read versus write ratio of your application. I can't think of anything off the top of my head where you would prefer this for a distributed setting. Maybe it's a little bit easier to have something like eventual consistency, where if your distributed nodes aren't necessarily all simultaneously updated, like you could have updates, trickle to replica nodes over time. This might be a little bit better because then you can just to apply the update, you just append a new record rather than trying to lock things in a distributed setting. But I don't think that there's any inherent advantage or would be any inherent advantage in a distributed setting. So you can build indexes that help you kind of navigate these log pages. Another option is you could periodically compact the log. So again, we kind of have all of these log records building up. We have to replay them in order to kind of reconstruct individual tuples. If we perform a compaction, we could get something that looks like this. Basically, we just squash down all of the log records into single values. So now we don't have to reconstruct tuple ID 2. We can just go and look it up in the page. So kind of we can perform this periodically, lock the page, make sure no one can do anything concurrently, and then perform this compaction and then release the locks. So kind of it simplifies things a little bit. We don't have to scan through the whole page again. We can just kind of go and look at the individual tuple values. So there are a whole bunch of systems that kind of take this approach versus the other slotted page approach that we talked about. It's become a lot more popular in the last 10 years or so. A lot of these systems are more recent. You may know LevelDB is from Google. RocksDB actually is from Facebook. They took LevelDB and kind of, the first thing they did is they ripped out mmap from LevelDB because, as we talked a little bit about last time, mmap has some problems. But so RocksDB is kind of a fork of LevelDB from Facebook, which they're currently using, or the idea was to replace the default storage engine for MySQL. They had a huge MySQL deployment. The idea was to replace the default storage engine for MySQL with RocksDB. And again, this is kind of taken off in the last 10 years, but the idea isn't new. There were papers published 20 or 30 years ago kind of detailing these techniques. So to go a little bit further into detail about how the compaction actually works, basically we just want to, as I said, coalesce or squash together these larger log files into smaller files by removing unnecessary records. So, for example, if you have a bunch of updates, you can just squash those down into one that specifies the value of the tuple. So the way this usually works is we perform this level compaction, where at level 0 is the top level. We kind of have this sorted log file that's building up, and we build up all these pages over time. And what we'd like to do is perform a periodic compaction. So perhaps when these two pages fill up, what we're going to do is squash them down into a larger file in the next level. So we take those 2 pages, kind of replay them to perform the compaction. We get this compacted, larger, sorted log file that's now in level 1. And again, more log files are going to build up in the top level, and we kind of just keep repeating this process, compacting the files into smaller single files, and eventually we get down to some bottom layer where everything is fully compacted. So you can think of it kind of like a merge sort or something, where you have these different runs that you've sorted independently, and now you want to merge them together into one larger run that's all sorted together. So kind of this is how the level-based compaction works. There's an alternative, which is called universal compaction, where basically what we do is we can just take any 2 adjacent blocks and merge them together like this. So rather than doing it in levels where we're specifically working from the top level that has these pages that fill up and then merging them as we go down, we can just start merging adjacent files in sort of a universal setting. And this is actually used by, it was created for RocksDB by Facebook. So there's no level concept here, we're just merging adjacent files. Okay, so that's it for page-based storage. So we kind of looked at, again, the slotted page-based approach and the log-structured approach. So that's kind of it at the page level. Now we're going to move on to kind of the next level down, which we started talking a little bit about last time, the data representation at the level of the tuple. If we have an individual tuple inside a page, how do we store it? How do we interpret the data that's stored inside of it? And how do different layers of the DBMS leverage or extract the data that they need from the tuple storage? So that's going to be the first piece. The next piece we're going to talk about is kind of system catalogs. So how does the DBMS as a whole store information about the data that's stored in tables? So if you want to know, for example, the schema for a particular table, like the student table, you need to know that students have an ID, a name, an email address, etc. How is that stored within the system? And then finally, we're going to wrap up talking about a few different high-level storage model alternatives. So again, I showed this slide in the last lecture. Just at a high level, a tuple is essentially just a sequence of bytes. So think about it, just a series of bytes stored inside a page that has some data in it, and the various pieces of the storage manager are going to tell us how to extract individual data values from that sequence of bytes. So the DBMS figures out, how it's going to interpret these bytes and give us values back. So the catalog, as I mentioned, is going to contain the high-level schema, which is just information about the tables. It's going to tell us, how exactly the bytes are laid out inside a tuple. So the different data types we have to worry about, these are probably the most common. There may be some other ones, and of course there can be user-defined types, but pretty much this is what you'd expect to be working with. So things like integers. There are different sizes, integer sizes described in the standard based on how many distinct value, like the range of values that they should be able to support. So those are integer, big int, small int, tiny int. Basically what these are stored as is their C or C++ representation. So if you have an integer that fits in there are 256 distinct values, you can store that in a single byte. If you have an integer in a larger range, you may need to use a 4-byte or 8-byte value. So basically, these map more or less pretty clearly from SQL data types to C or C++ data types. Floating point values are a little bit trickier, and we'll talk more about those in detail, but essentially for floating point values, you can think about things that you would store in a 32-bit or 64-bit floating point. Numeric and decimal types are special fixed point decimal types, which we'll cover in the next slide. So in varchar, var binary text are all basically just variations on strings. So usually they are stored as some kind of header that specifies the length of the string, followed by just a series of bytes that represent the string data, the character data. Sometimes I guess you could also store it as null terminated, like in C or C++, you'd store it as a null terminated string, but most systems I think implement it with this length header followed by some number of bytes. And then finally, time, date, and timestamp I think were pretty important in the homework. And basically, again, this is just, you can think of it as like a 32-bit or a 64-bit integer that stores a number of seconds or microseconds or whatever it is since the Unix epoch, so January 1st, 1970. And you can kind of convert that back and forth from this integer value to a date. So kind of the trickiest one I mentioned is floating point values or numeric values. So these are arbitrary precision numbers, and they're kind of the most difficult to deal with. So we're going to talk about some kind of specialized ways that systems tackle them. So kind of the big problem with variable precision numbers is that they're inexact, and they have they're difficult to represent in computer architecture. So as you may know, like floats or double data types in C or C++ are approximate representations of decimal numbers. And this is the IEEE 754 standard, kind of specifies how they should be stored. And they're typically faster than kind of these arbitrary precision numbers that we're going to implement, things like decimal type or numeric type that we're going to implement in the database management system, but they can have rounding errors is a big problem with them. So, if you think about something like, I don't know, you're just collecting maybe like temperature data about my office or something, a little imprecision in that might be okay. I probably don't need finer grain values than, whole degree numbers, but if you're storing data that's like, I don't know, the balance of your bank account, you might care if there are going to be rounding errors. So kind of just as an example of what this looks like, this is just a really simple C program. Basically, we just have these two floats, x and y. X is 0.1, y is 0.2. The first print statement is going to just print the sum of x and y. So it just prints out 0.1 plus 0.2. And the second print statement is just going to print out the value 0.3. So who can tell me what the result of this, if I compile and run it, what's it going to look like? It's not a trick question. So the values that are going to get printed out, this is the output. You can try it on your own machine. So x plus y gives 0.3 with a bunch of zeros after it, which is what you'd expect. And printing out the constant value, 0.3, also gives 0.3 with a bunch of zeros after it. That looks fine. But if we specify that we want more precision in our program, so here it just changed the print statements to control the number of significant digits that get printed out. What we end up with is something that looks a little bit different. So The first one, x plus y, 0.1 plus 0.2, I think we can all say that that's not quite correct. After several zeros, we get kind of this garbage at the end. And also printing out 0.3, 0.29999 is not quite 0.3. So again, depending on the type of data you're working with, you can tolerate a little bit of imprecision. These floating point values might be okay, and they'll be fast. But if it's something important, like a bank account, that you want to make sure you get the values right, we can't tolerate this loss of precision in the database. So that's going to force us as the developers of the DBMS to implement numeric data types that have a fixed amount of precision. So we guarantee some level of precision in the data types that we implement. It could be potentially arbitrary, precision and scale, and we want to use these when rounding errors in the data are unacceptable. So the data types are numeric and decimal data types. And there are many, many different implementations of how exactly these things work in real systems. Typically, the commercial ones are much more sophisticated, since they know, business applications have a lot of need for fixed precision numeric values. So they typically have pretty sophisticated implementations, but kind of there's no hard and fast way that all systems implement this. Everyone does something a little bit different. But kind of again, the trade-off is that to ensure the amount of precision that you need is going to require more overhead in your processing. So you're going to have to be more careful than just using the basic 32-bit, 64-bit floating point values that C or C++ provide to you. So just as a few examples, we'll look at first what Postgres does to implement their numeric data type. So this is the struct that they specify in their code. So we can look at the different pieces. Basically, you start out with the number of digits that you have in your numeric data type, the weight of the first digit, the scale factor, whether it's positive or negative or a nan, and then the actual digits themselves. So that's the last piece there. And if we kind of look at what that actually is implemented as, numeric digits are basically just a char array. So it's just char bytes stored in some variable length array that we can use to decode these individual values. So if we look at now how the code to actually handle this looks, if you have a floating point value, it's just one instruction or whatever to add them together. All of this, and it's cut off at the bottom. You have these nested if statements, switch statements, all kinds of stuff going on in there, just to add two of these numeric data types together. So you have to check what's the sign of the first value you're trying to add, what's the sign of the second value, and all this kind of stuff this has to execute every single time for every single tuple where you want to add these two values together. So you can see this quickly gets a lot more expensive than just using floating point values. Yes.
So adding floating point numbers is also pretty complicated, but we have dedicated hardware that does it. Has anyone ever tried making dedicated hardware or dedicated processor instructions for adding fixed point numbers?
So the question is, floating point values are fast because there's dedicated hardware for it. Has anyone ever tried making dedicated hardware to add fixed point values together? The short answer is I do not know. There could be, especially in other communities outside of data management, things like hardware, software, co-design. There may be research that looks at that, but I'm personally not familiar with any of it. I don't know. It's an interesting question, since there are some DBMS vendors that have tried to fabricate specialized hardware for their DBMS product, but I am not familiar with anyone who specifically has designed any piece of hardware to do this fixed point addition or computation in general. But I can look into it and get back to you next class.
Thank you.
Sure. So that was Postgres. This is MySQL. MySQL, this is their numeric type. This is the struct that defines it's a decimal. And again, we have these pieces that tell us the number of digits before the decimal point, after the decimal point, the length in bytes of the value, the sign, whether it's positive or negative, and then the actual digit storage. And again, kind of similar. This is stored as int32 rather than just a char array. But the end result is the same. Basically, you're storing this variable length array of digits that you then need to decode, again with all of this difficult logic. So this is the add function from MySQL, or subset of the add function from MySQL. And again, you're kind of going through and doing all of this complicated if-else conditional, switch statements, all kinds of stuff to check and to perform the actual computation by decoding the values that are stored in the data array. So does anyone have any questions about kind of the fixed point arithmetic before we move on? Great. Okay, so the next piece that I want to talk a little bit about is for large values. I think someone in the last class asked either what happens if an individual value is too large for a data page, or if an individual tuple is too large for a data page. I think I said that there's nothing in theory stopping a tuple from spanning multiple pages, or a value, an individual value, from spanning multiple pages. I think most systems don't allow a tuple to exceed the size of a single page, so it's constrained either in the size of the columns or the number of columns or both. And you're not able to specify a single tuple that's going to be larger than one page. So now the problem comes up is, what if we have individual values that are larger than a page? So imagine a really long string or something. The way that we store that is in what's called an overflow page. So basically, we're just going to take the individual tuple that we have, and we're going to specify the value. In this case, C is a really large value, and it's just going to point to the varchar data that's stored in this overflow page. Now, of course, maybe that's again too big for the overflow page. So this could, in theory, span multiple pages. You could just point to a chain of pages to have an arbitrarily large varchar value. So this is called different things in different systems. Postgres calls it toast, which these overflow pages are going to kick in if the value is greater than 2 kilobytes. MySQL, I think it's greater than half of the size of the whole page, or in SQL Server, if it's greater than the size of a page, then this is going to kick in. So kind of an alternative way to handling these large string objects usually is to store it externally to the DBMS. So kind of, we talked in earlier lectures about why it's a good thing for the database management system to kind of have full control over all of the data, so it can understand everything that's going on, manage the safety and all of the properties we want to apply or to ensure for the data. If you get sufficiently large data, there are certain cases where you may want to have that stored externally to the DBMS. So some systems let you store this type of really large file in what's called the blob, binary large object. So and the different systems call it different things. I think it's called a B file and Oracle file stream in Microsoft. But basically, the way the blob works is you just store, again, sort of a reference in the tuple, and that's going to point to some external object. So can anyone think of a use case when this might come in handy? What sort of data might you want to store external to the DBMS? Netflix is a good example. So basically, like multimedia data, images or videos that kind of don't fit well with the data model in our DBMS. If you think you have an individual Netflix like video file, movie file, that can be gigabytes, so that doesn't fit well in our DBMS, so we kind of just store a pointer to that data, and it lives somewhere else on the file system, and we can reference it when we need it. The drawback is that there's no explicit durability protection, so since it's outside the DBMS, we can ensure that it's stored safely. The part of the guarantee that we get from the DBMS is that if our data is inserted, then it's going to be persistent. We're not going to lose anything, but if it's stored externally, there's no way to control for that. And also there's no kind of transactional protection. So if you have some other program that's concurrently modifying the file, we can't guarantee that it's going to be in a consistent state when we go to read it. So a question you might have is like, when do you want to take this approach versus when to store something physically inside a DBMS page in one of those very overflow pages that we talked about. So outside of different types of files like images or videos that don't fit well with the processing model we have, kind of the other reason you might want to do this is if you just have a large enough, and by large enough, there was this paper that came out. This is from Jim Gray. I think I mentioned him before. He's a famous database researcher. He won the Turing Award. And this paper was kind of evaluating the size of when it's more beneficial to store a blob directly inside an overflow page versus externally. And kind of the conclusion they came to, I think this is about 15 years ago this paper came out, the conclusion they came to was about 256 kilobytes is when it's more beneficial to store externally, because again, remember, we have to, if it's stored inside the DBMS, inside the database, then we have to read pages, and we get these huge objects written to and from disk every time. So kind of that's the trade-off that they figured out, and the exact numbers may be different now, but kind of thinking at a high level, there may be cases when it's more beneficial for you to store it directly inside the DBMS, other cases where it's more beneficial to store as an external object. So the next piece that we're going to talk about is the system level catalogs. So in order for the DBMS to know what's going on with the data stored in the database, it keeps all sorts of metadata about the database internally, so it can perform different tasks. So as I mentioned, one of the most important things is we need to know how to encode and decode the data that's stored in the just bytes that represent tuples. So we store information about tables, columns, indexes, views, all that kind of like structural stuff. DBMSs typically also store information about users and permissions, so like access permissions, which users should be able to view or modify which pieces of data. And finally, they keep around a lot of internal statistics, so things like the number of distinct values or join cardinalities or data ranges, things like that, which are going to be really important for query execution, which we'll talk about in later lectures, things like planning the most efficient way to execute a query. It's helpful if you know statistics about the data that you're storing. So almost every DBMS that I know of stores the database's catalog like inside of itself. So it basically just stores it using the same abstractions, things like tables, indexes, that kind of stuff, that it uses to store regular data. So now the problem is there's like this chicken and egg problem where if we need to write a SQL query to query the metadata, but we need the metadata to answer the SQL query by decoding the values or referencing objects, it's not clear where we would start. So kind of what systems do is they have these kind of special wrappers around metadata objects that the system can use to directly encode and decode the values stored as part of the system catalog. So they like bootstrap the catalog tables in that way. So you can, as the user, can query the DBMS's internal catalog. It's usually stored in this information schema to get information about the database. You can see all of the objects that are stored in the database. It'll tell you information about tables, metadata, statistics, all kinds of stuff. And it's defined as by the ANSI standard as this set of read-only views that are going to provide information about everything you need to know that's stored in the database. And kind of before this was standardized, it was sort of a mess where every kind of system had their own way of exposing the metadata. So kind of to make it more manageable and portable, they codified it in the standard so that all of the systems are exposing the same metadata to the users. And there are also like a lot of non-standard shortcuts. If you were playing around with SQLite at all, you may have looked at some of those to kind of show what tables or data was stored in the schema. So just I'll show a few examples. If you want to list all of the tables in the current database, you can write it as this SQL 92 compliant query. We're saying select star from information schema.tables, and you can get the table catalog is the name of the database that you're interested in. And these are just some of the shortcuts that different systems have. So in Postgres, you can just do \d. MySQL is show tables, and SQLite is .tables. So again, to get the schema for just an individual table, you want to get all the information from student. You can, again, select star from information schema.tables, where the table name is student. And again, there are all these different shortcuts in the different systems where you can get the same data that's provided by the standard SQL query. Okay, so are there any questions about schemas or catalogs before we move on to the last part of the lecture, which is about the data storage models? Okay. Okay, so kind of an important piece to talk about before we actually look at the different storage models, high-level storage models, is to talk about the different types of database workloads that we can have. So the first one we'll talk about is what's called online transaction processing, or OLTP. And basically what this means is that you have a lot of fast, short-running operations that only access, so either read or update a small amount of data each time. So you can think about that as like your bank account. If you want to get the balance of your bank account, you're just reading one value, or if you want to do a transaction, deposit money, withdraw money, it's a fairly short transaction. Another way to think about it is something like an online store like Amazon or something. You go through, browse different products, add them to your shopping cart, check out, pay, ship, and the amount of data that you're accessing relative to all of the products that Amazon offers is relatively small. So you're just buying a few individual products. But if you think about all of the people around the world that are concurrently making purchases, then it starts to add up. So kind of the amount of data that is accessed or modified by individual transactions, so your individual purchases, is relatively small, but taken in aggregate across all of the concurrent transactions, it can get quite large. So that's online transaction processing. The kind of other side of the spectrum is what's known as online analytical processing, OLAP or OLAP. And basically, these are kind of like analytical queries that read lots and lots of data. So they scan whole tables, they produce aggregates, there are lots of joins. These are used typically in things that are like decision support or business intelligence. You kind of want to look at all this data that you've accumulated and see if you can get any insights out of it. So you're executing these large-scale queries that provide you some type of useful or meaningful answer. This is kind of similar to like what the homework assignment was. You wanted to figure out certain high-level information about different products, or answer queries like in the Amazon example, maybe Amazon wants to know, okay, what are the top 5 most popular products purchased in the past month by CMU students. So kind of you want to scan a large sample rather than just updating individual or reading individual records. You want to scan a large sample and see if you can get any useful insights out of it. So these typically are longer term, long-running queries. They might happen overnight, or they might be run to populate like a report or something that you give to a higher level executive or decision maker. And they're oftentimes a lot ad hoc. So they're not queries that are repeated a lot, unlike transaction processing. Every new order transaction that gets sent to Amazon basically has the same template. The OLAP queries are usually kind of one-off, ad hoc, and more specialized. So that's kind of, on the one side, you have OLTP, OLAP on the other side. There's this new buzzword thing that's becoming more popular recently. It's called Hybrid Transaction and Analytical Processing, or HTAP. And basically, the goal is to be able to do OLTP and OLAP together on the same database instance. So you have essentially your transaction processing and your analytics running concurrently. Hopefully you can get, the idea is you'd be able to get faster or more real-time insights about the transactional data that's coming in. So if you think about kind of the spectrum here that you have, on the x-axis is the workload focus. OLTP is more heavily geared towards writes. There are some reads, obviously, that you need to do, but think about, the ordering a new product. You want to insert information into the table that you ordered it. You want to insert information about your shipping address. Maybe update some aggregated data that Amazon stores about you. Whereas for the analytical queries, they're more heavily read focused. So they're going to spend a lot of their time scanning a lot of tables, performing a lot of joins to kind of get the data together that you need for the analysis. Then on the y-axis, there's the notion of operation complexity. So how complex is the query or the program that you're running for each of these workloads? So again, OLTP is towards the simpler side, just inserting new records, updating individual values in tables. Like maybe you update your payment information or your shipping information. That's just changing a few values in fields. Versus on the other end, OLAP is usually a lot more complex, again, joining many tables or performing complex aggregations windowing functions, all that kind of stuff that you saw in the homework. And again, kind of this HTAP sits somewhere in between. You want to do both of these things at the same time. So the way that this usually looks in practice is a company an organization will set up these kind of two separate environments. So on the one side, you'll have usually multiple OLTP data silos. You have all of these database instances running, accepting concurrent connections from different clients to perform the transactional side of the workload. And then on the other end, you have this really big OLAP data warehouse where you're going to want to dump all of your data for analysis. So again, we kind of have all the transactions running on the OLTP side, all inserting or updating or whatever their operations are on the individual silos. And then we're going to go through this process. It's usually called extract, transform, load, ETL, where we take all of the data out of these different silos. It may be formatted differently. There may be redundant data. So for example, you could have two students you could have a student stored in multiple databases that has the same name. So it could be like my name, Andrew, and Andy. One is just my nickname, or Drew. And you want to kind of merge these records into a single logical record during this ETL process to get them cleaned and ready and formatted to go in the data warehouse. So kind of this ETL process might run overnight or periodically throughout the day. We kind of gather all of the data from the different siloed OLTP databases, format them, and then shove them into this data warehouse where we're going to run different analytical queries. So again, kind of based on the results of the analysis we perform, we might want to push some data back out to our OLTP data silos. In the Amazon example, maybe we run the analysis to figure out what products the CMU students have been buying. So then we want to push back from our data warehouse to the OLTP side product recommendations when you visit the web page for what to buy. So again, kind of the idea of moving the analytical queries and having them execute concurrently with the transactional workload is what this HTAP idea is about. So kind of why is all of this important? Why does it matter that we have these different types of workloads? Well, if you think back to the relational model, it doesn't really specify, how we store the data. It, gives us certain rules and requirements for the different operations we should be able to perform on the data, but it doesn't tell us how physically we need to store the data. And in fact, as we've seen, a lot of different systems store the data in all sorts of different ways. There's, the different page layouts, slotted pages, log structured pages, all different kind of options there. There's all different kinds of options in storing individual data types. But going a step further, there's nothing that says that we have to store kind of a tuple's attributes together in a single page, like as consecutive bytes, as we've been doing. So I think I mentioned early on that kind of there's this notion of a row and why that might be different from a tuple or a record. And that's because the row storage layout assumes that all of the different attributes in a tuple are stored consecutively. So again, if you have the student record that has ID, name, email address, you'd store all of those in consecutive values. So based on those different workloads that we talked about, OLTP, OLAP, the row layout might not actually be the best for all cases. So I'll kind of go through and explain what that means. And just as an example, we'll use this simplified version of the Wikipedia schema. So that it's just cut down to 3 tables. Basically, you have a user account, which is, you know, the Wikipedia users. They have a user ID and a name. You have the different pages, which store the Wikipedia data. And then you have a revision history, which says which edits or revisions were made by which users to which pages. So kind of those are the 2 references there. User ID references the user account table, and page ID references the pages table. And I'll point out there's this one other cyclic reference here from pages back to revisions. Basically, it's just if an optimization that Wikipedia does is if you want to get the most recent revision for a page, is they store it right in the page. So if you think about kind of the OLTP types of queries that we might be running against the Wikipedia pages, again, it's just simple queries that read or update small amounts of data. So usually single entities. It might be things like, you know, getting the page data. It might be updating when the last time a user logged in, or it might be adding a new record into the revisions table. So just kind of these really short-running, simple operations that only read or write a few values in the database. And this is, you know, if you have a new company or a startup or something, this is usually the type of application that people build first. So you kind of have these transactional things for your new app or whatever that basically manage the simple aspects of the application. So kind of on again, the other side, the analytical side, we're issuing complex queries that read large portions of the database. So in this example query here, we're counting the number of distinct logins over the last month from users where the host name is like .gov. So where you have people logging in from .gov. This example is just from there was a scandal 10 or 15 years ago where politicians were having like staffers log into their Wikipedia pages, and they would have them remove unflattering or scandalous things, or a whole bunch of people, is like Mike Pence, Joe Biden, I think, a whole bunch of people that were having staffers do this. So kind of if you wanted to know how many times staffers were logging into Wikipedia and making these types of edits, you could issue this kind of like analytical query against the data that you collected on the transactional OLTP side of things. So all of those revisions that we were adding, so revisions or logins or those types of things that we're adding, you can query those later to get insights out of them. So again, I hinted that this was leading towards discussion of storage models, and the key piece behind this is that we can store tuples differently behind the scenes, so without exposing this to the application or the user, that are perhaps better for either OLTP or OLAP. So kind of what we've been talking about so far with this row-based storage model, where all of the values are stored consecutively, is what's referred to as the n-ary storage model. So again, that's this row format where everything is just like an array of bytes where everything's stored consecutively. So again, everything's contiguous in a page, and it's in particular ideal for OLTP workloads because queries tend to operate on individual records, or in this case, rows. So if we need to read or update an individual row, we can go grab it. And everything is stored together in a row format. If we want to do an insert, we just insert now a bunch of contiguous values that are all stored consecutively together in a page. So kind of this is the classic way we've been talking about this. You know, if we want to get tuple number 1, everything's stored together right there in the page. We have the header and all of the different aspects of it. And again, if we want to get any of these other tuples, we can just go and access all of the values together. So each of these pages are stored like this in a row-based format in the database. So this is kind of exactly how we've been talking about database pages so far. And again, if you just want to execute this simple query, says login query or something, we're going to load their profile. We need to go and get all the information about the user account from the user account table. So what we're going to do is we're going to send this query to our system. It's going to hit an index. So we haven't talked about indexes yet. We're going to talk about it in lecture 7. But basically, you can think about an index kind of like a page directory where you know, the page directory maps page IDs to like physical locations. The index is going to map values, so like in this case a username or something, to a page ID and record ID pair. So this query is going to go to the index. The index is going to tell us, okay, hey, go get this page, and then it's going to tell us which tuple exactly to locate in that page. So, and again, if we want to, you know, insert something, it's pretty straightforward. We just now add a new row in that page right there. So, kind of, this is exactly how we've been talking about database storage models so far. So that was the OLTP side. If we come back again to this query to get all of the logins from .gov hosts, we can kind of see how this works in a similar way. We're going to go, you know, get all the pages. We have to scan through all the pages because we don't know where, you know, what exactly we're looking for. We just want to look at all of the pages in the database. And we're going to go through and perform first the filtering. So where the host name is like .gov. And that's going to require us to look at the values in that column, the host name column. And then the next thing that we're going to do is we're going to have to go and look at this last login piece to do the count and the extract part of the query. And that means we need to look at the values in that attribute there. So the big problem here is that what's going to happen with all of these other columns that we don't touch? We don't need to look at them for this query. They don't have any impact on anything that we're doing. So kind of it's just useless data that we're having to read in from disk, even though we're not looking at it or touching it at all. So kind of to summarize, the NRE storage model has these advantages of really fast inserts, updates, and deletes. And they're good for queries that need to access the entire tuple. So again, you know, loading your whole profile, when you log in, we need to access all the data in the tuple. But there are disadvantages, like in that previous query I showed. They're not good. They have a problem with scanning large portions of the table or subsets of attributes, because what you're ending up doing when you read a whole page is you're reading in, you know, a bunch of columns or attributes that you don't need when there's no need to, because they have no impact on reading the query, so they're eating up your I/O bandwidth, file I/O disk bandwidth with no benefit. So kind of the alternative approach to this NRE storage model that we can take is what's called the decomposition storage model, or DSM. And basically what we're going to do is the DBMS is going to store the values of a single attribute for all tuples contiguously in a page. So rather than storing all of the different attribute values for a single tuple contiguously, we're going to extract all of the attribute values for a single column, which is where the name column store comes from. We're going to extract all of those values and store those contiguously for several tuples. So this is ideal for like OLAP workloads where you have a lot of read-only queries. You don't have to do many updates or writes in general. And you want to perform large scans, particularly over subsets of the attributes. So if you have now all of the values for a particular column stored in one page, you only need to read that page. You don't have to worry about the other useless columns that don't get used in the query. So Again, as an example, if we go back here, what we're going to do is store each of these attributes individually in a page. So as an example, let's say the host name page, we're going to store the host names for all of the tuples together all in one page. And again, we're going to do the same thing for user ID, last login, username, whatever the other attributes in the table are. So, you know, they're probably, if you have enough data, you'll end up with multiple pages. But the point is that for each attribute, for each unique column in the table, we're going to store the values for all of those columns all together consecutively, contiguously. So now again, going back to this query, we only need the host name and the last login. We don't need any of that other stuff, any of the other attributes from the table. So we can just now go and get the pages that specifically correspond to those two columns. We don't have to worry about the other columns. We don't have any wasted bandwidth. We can just go get those specific pages that we need for those columns. Yes?
In the textbook, it mentioned that there's also some sort of storage model where you would break up a single relation based on like a year. So maybe accountants are concerned about this past year that things from 10 years back and are worried about, so you might break it up that way. With what storage model would that fall under?
So the question is, if you had some kind of partitioning strategy where you split up the data into, let's say it's organized by year, and you want more recent data grouped together, so you can sort it by year or something, and then partition it that way, so you only get the most recent data versus older data you might not care about. What storage model would that be under? So I guess it's orthogonal in some ways to this row versus column layout. I think it's kind of like, so for example, you could have, you could take your row-based data in the n-ary storage model, and you could sort that by year and partition that by year, so that way you still get kind of the temporal locality for the data items. You could do the same thing with the columnar storage, or the DSM. You could sort columns by, you could sort the whole data by year and partition it up that way. So I think it's just an additional optimization that you could apply if you know that there's some kind of, for example, temporal locality. Another way you could think about it is if you have different regions, like continents or something. You have European clients and North American clients, Asian clients, whatever. You can partition your data that way. So I think any sort of partitioning scheme or strategy that you apply on top of this is orthogonal to the row versus column layout. Does that answer your question? Great. Are there any other questions about kind of this n-ary versus DSM trade-off? So the next piece that we need to worry about in kind of the DSM implementation is how are we going to, I've told you that we're going to split up the tuples into individual column values and store all the column values together. How do we reconstruct an individual tuple? Like how do I get back to, if I have the username and the email address and all that stuff split up, and now I need to query an individual student, how do I get that back together to reconstruct the record? And the answer is there are two different ways that are typically applied. I think the offset-based one is more common, so I'll talk about that first. So the idea is that you have these fixed length offsets that you can apply because individual column values all have the same type. So for example, let's say user ID is just an integer. We know that's 32 or 64 bits or whatever it is. So in order to access the nth value, we can just figure out, okay, that's 32 bits times n gives us the offset of the ID in that column. At the same time, if we want to go and get the email address or something, you can kind of just jump directly into the corresponding offset in the email address column. Now, you might run into a problem if you have variable length strings. There are different ways around this. One is, you can pad out strings to a particular length. If you have a lot of repetition in the strings that you store, you may be able to do some kind of encoding, like a dictionary encoding, where you replace strings with just a fixed length integer code. We're going to talk more about that kind of stuff in later lectures, but kind of the key idea is that if you split things up into columns, you can use these positional offsets to jump directly to the offsets you need to reconstruct individual tuples. The other option, again, is to kind of store the IDs for individual tuples embedded directly in the columns themselves. So rather than storing columns individually, you now have like these joint columns where you store first the ID followed by whatever the data value is that you have. And here they're all sorted in the same order, but you could imagine, you could have individual columns sorted in completely different orders. And then use the tuple IDs to reconstruct them. So you might ask, why do I want to sort columns in different orders? Again, we're going to talk about this in later lectures, but it may allow you to apply better compression. So for example, if you have sorted data in a particular column, you might be able to get better, like for example, let's say it's dates. If all of your dates happen to be, just one day apart, you may be able to store some like delta encoding where, rather than storing the full date, you can just store a much smaller value that says this is just one day, add 1 to the previous day. And you can get kind of a much better compression. The other thing is, again, if you have sorted data that lets you do binary search or some more intelligent search for individual values than having to scan the whole column with like a sequential search algorithm. So those are kind of the two ways that you can rebuild individual tuples. So just to summarize, like for the n-ary storage model, the DSM has advantages and disadvantages. Obviously, DSM reduces, as I mentioned, the amount of wasted I/O because you only read the data, the columns specifically that you need to answer your query, and you can get better query processing and compression for the actual stored columns. The disadvantages are, it's slow for point queries, so if you want to go and reconstruct an individual tuple, it's a lot easier if you just have it, laid out contiguously as a row. But here you have to kind of do some reconstruction, either using the offsets or using the IDs as in the previous slide. And it's a lot harder to do, inserts, updates, that kind of stuff, because you have to go and, add now values to multiple columns, multiple pages, rather than just writing all at once. So DSM systems are not new. They've been around for a while. The first one I know of is from the 1970s. It's not actually like a DBMS. I think Cantor's a file system, but basically if you look at what they're describing in the paper, it's a column store. In the 1980s, there were the first, theoretical underpinnings or proposals for DSM storage. In the 1990s, there's a product called Sybase IQ. It's like a in-memory accelerator for the Sybase row store. I don't think it ever became that popular, but kind of what they were doing was storing the data in memory in a columnar layout to accelerate certain types of queries. It really took off in the early to mid 2000s with these three systems: Vertica, VectorWise, and MonadDB. If you're interested, you should check them out. They are kind of the first popular and commercially successful column stores that really paved the way for a lot of the techniques that are now commonplace in columnar storage. And it says 2010's everyone because pretty much everyone, and this is not everyone, but this is a small subset of everyone, pretty much everyone nowadays has some columnar storage option if you're in the analytics or OLAP market. So pretty much if you have a row-based storage, n-ary storage model for analytics, you'll get crushed. So kind of everyone implements, including big commercial systems like Oracle implements this kind of columnar storage model for the analytics type queries. So just to wrap up, I kind of have been talking about a DBMS as having a stack comprised of these independent pieces. As we've seen, they're not entirely independent, and sometimes you need to know about certain other layers in the stack. So for example, the storage manager might need to know about kind of the higher level application pieces in order to pick, you know, n-ary versus DSM versus some other partitioning strategy. So kind of, there's not always necessarily this clean cut between layers in the stack. And it's really important to choose the correct storage model for the workload that you're targeting. So just as a high level piece, if you got nothing else out of this lecture, just remember OLTP, you want row storage, and OLAP, you want column storage, because otherwise you'll get crushed. So for next class, we finished today, last lecture and today, the problem number 1, which is how the DBMS represents the database and files on disk. And next class, we're going to talk about how you move disk pages back and forth from disk to memory. And that's going to be the topic for the first project, programming project, the buffer pool. So thanks, and I will see you on Wednesday.